to do is talk about the interior of the sun, the surface area of the sun, and what we see, and then how it affects Earth. So we're going to start with the interior workings of the sun. It's really hard to figure out in some cases because, after all, you don't see the inside of the sun. You see the outer parts of it, and you have to figure out what's going on inside the sun from what we do see. And now some things we can figure out on the inside of the sun by mathematical analysis, because we know what the sun's made out of. We know it's made of hydrogen and helium, and we can study in the laboratory the physical properties of hydrogen and helium. And from that, we can calculate what's going on inside. We do have a pretty good idea about the basic structure of the sun. And the basic structure of the sun is that from the center outwards, about a quarter of the way or so, is the core of the sun. That's where thermonuclear reactions are going on. That's where the energy is being produced in the sun. And then above that, stretching from that point outwards to about 2/3 of the way out, is the radiative zone. And again, unlike in a lot of diagrams where the energy is just radiating out, it's really bouncing around, bouncing off of things that's going. And so it really takes thousands, tens of thousands of years for the energy to make it up to the top of the radiative zone, bouncing around all over the place. Once it reaches the top of the radiative zone, it heats gas, which then expands, rises, and then cools off and sinks. And so that is the convective zone. And so this allows us to pick out the major aspects of the sun, the major areas of the sun here. I just like this diagram right here because it's dynamic and it actually shows stuff moving. Again, the radiative region is not quite right, but it does illustrate another important part, and that is in the convective region, there's actually complex convective behavior here, in that you have some major convective cells, and then you have some smaller convective cells on top of that. And that actually gives rise to some of the features that we see on the surface of the sun. Stellar models are our mathematical description of what's going on inside the sun. So the stellar models, we go through the mathematics of everything, and we realize that near the center of the sun, you have a temperature that's ballparkish about 15 million Kelvin. And then as you work your way out, the temperature drops and drops and drops. Now, it drops sharply because you're producing energy in here, and the further out you are, less energy you're producing. But this drop is part of the reason that you don't get convection in here. This is kind of like you sometimes in the DFW area, and you have the sunlight heating the ground, the hot air rises, and then when it rises high enough, you can get a thunderstorm. When the summertime, there's often a cap on it, and so that means the convective potential in there, it rises for a little bit and stops. And so if it doesn't keep rising, then you don't build the big thunderstorms and you don't get rain. So here you have this drop of a temperature. So as the gas in here is so compressed, it goes up, it expands. Now it's cooler than the surroundings, and then it sinks, and so it doesn't convect. In the outer part here, it's a little bit different. You have more of a flat sort of temperature gradient, and so you heat the gas, it expands, and then as it rises, it's cooling off a little bit, but it's not cooling off as quickly as what's out there, and so you get convection in there, and that tends to smear out the temperature in there. Density. Near the surface of the sun, or what we call the surface of the sun, the density is pretty low, about 0.1 kilograms per cubic meter. That's actually less dense than air. The air that's around you is a little more dense than that. So this is pretty thin. Near the center of the sun, it's about 150 metric tons per cubic meter. So what does that mean? It means that under your typical dining room table, you might have a couple, it might be a couple hundred metric tons worth of material if that was at the center of the sun. Well, so look at the volume under a dining room table and imagine that being a couple hundred metric tons squeezed under there. Well, that's denser than gold by far. Now, think about it. This is mostly hydrogen and helium. So what would hydrogen and helium be like if you squeezed it that much? And the answer is it's not going to be like any substance that you know. So the hydrogen and helium at the center of the sun are going to behave way differently than what you normally think of as hydrogen and helium. It's a different state of matter. It's a plasma. So it's not really solid, liquid, or gas. It's plasma. So it is in fact something a little bit different. There are more states of matter than just those three you normally learn in elementary school. Luminosity, that's how much energy is passing you. So if you're a tenth of the way out from the center of the sun, then a little less than half of the sun's energy passes you. If you're about a fifth of the way out from the center of the sun, then maybe about 80% of the sun's energy passes you. By the time you get out to about a third of the way from the center of the sun up here, then you end up with pretty much all the energy of the sun passing you. So any further out that you go, you have the total energy of the sun passing you. And so what that's telling you is that all the nuclear fusion is happening in the innermost one-third of the sun. Mass. By the time you get about 60% of the way out, then most of the sun's mass is below you. And so from that point on, then it's getting thinner and thinner and thinner. Okay. So what's going on in the center of the sun? Well, it's nuclear fusion. We know that now, but we didn't know that originally. Source of energy of the sun. And they had all these ideas about it. You know, the very first idea, and it goes back to ancient times, ancient Greeks thought about this. And they say, well, the sun is bright and the sun is hot. And so if the sun's bright and it's hot, then that's going to represent nuclear, or rather, that's going to represent fire. And so the idea was the sun is made of fire. A chariot and his flaming chariot. Or rather, Apollo and his flaming chariot. So the sun's made of fire. And that idea held out for a really long time, but during the Enlightenment age, scientists started studying chemistry and how chemistry works, how fire works. Fire is a chemical reaction. And they began to realize that chemical reactions can't explain the sun because the chemical reactions would burn out rather quickly. That the sun would only be able to shine for a couple thousand years or so, and there was clear evidence the sun was shining longer than that because we actually had historical records, you know, from ancient times when people looked up and they saw the sun. And the other thing is the chemical reactions would slow down as you went, and so the sun should be vastly cooler than it is now if it was reasonably hot in the past. And so that means that burning or chemical reactions don't cut it. The other thing is that what you need for fire is you need fuel, you need oxygen, you need heat. Well, the sun definitely has heat, has fuel, you've got the hydrogen, no oxygen. So that means that burning is, well, we can eliminate that as an idea. The next idea that actually William Herschel came up with was meteorite impacts. So William Herschel started his studies here of the sun, and this was about the time that they were beginning to realize that meteorites can run into Earth, and the release of all this energy of meteorites hitting the Earth, they realized that the sun is the biggest thing in the solar system, so maybe it has all this gravity just pulling all these meteorites in. And if that's the case, maybe all those meteorites hitting the sun would keep it hot. And Herschel and a couple others actually did some mathematical analysis here, and they suggested that it's actually possible that just the gravitational release of all these things running in could keep the sun shining for maybe 10,000 years. that predated historical records, and so they felt kind of comfortable with that. But that didn't seem that still didn't seem to work all that well. And in fact, we now know that that's nowhere near good enough. And so that idea doesn't work. And so Kelvin-Helmholtz contraction, we talked about that before. Kelvin and Helmholtz, two greats in thermodynamics, came along, and they said, well, maybe it's this gravitational release, that you have this big ball of gas and gravity squeezes it, that heats it up, radiates energy into space, but that heat produces pressure, tries to keep it from squeezing, stops it from squeezing. But then as it radiates energy, there's less pressure. You have the ideal gas law. And so that means it squeezes a little bit further, produces more heat. And they calculated that Kelvin-Helmholtz contraction could last for millions of years, even tens of millions of years possibly. And so they thought that way predated any kind of idea that anyone at that time in the 1800s had for the age of the Earth. Again, 1800s, the general idea was Earth may be tens of thousands of years old. And so that idea kind of like seemed to like put an end to it. And then they realized, no, Earth's much older than that. And they started realizing just how old dinosaurs were. They started finding dinosaur fossils and realizing the dinosaurs, dated back to tens of millions of years, many tens of millions of years. The fossil record goes back even further than that, hundreds of millions of years. And the realization that Earth is billions of years old. And so Kelvin-Helmholtz contraction definitely cannot be the source of energy of the sun, because they knew that the sun had to be at least as old as the Earth. And probably older. And so the next question was, something else is happening, and so they realized it's got to be some other kind of physics other than what they were dealing with. But no one knew what that other kind of physics was. And then ultimately Albert Einstein comes along, and in his work on special relativity, he derives that E equals mc squared. Energy and mass can be equivalent. And this was a fantastic idea that led, among others, Hans Bethe, Arthur Eddington, and Walter Baade, and many, many others to investigate this. And that led us to the idea that nuclear fusion, hydrogen fusing into helium, is the energy source of the sun. And they realized that could last for over 10 billion years. There's evidence the sun's nowhere near that old. So sun is at best only about 5 billion years old. So it's only lived about half of its life. And so this gives us plenty of time to explain what's going on inside the sun. And so that gives rise to nuclear fusion. So E equals mc squared, 4 hydrogens become a helium. Okay. Each one of those releases quite a bit of energy, a very, very tiny little bit of it, quite a tiny bit of energy, but there's an enormous number of hydrogens in the sun, and so all told, they release enough energy to keep the sun shining. In total, every second, 600 million tons of hydrogen fuses into 596 million tons of helium. That means every second, 4 million tons, every second goes poof, ceases to be mass, and becomes energy. That's more than enough energy to let the sun last for between 10 and 12 billion years. And so that is the basic idea of nuclear fusion inside the sun. Now, unfortunately, it's not that simple because hydrogens are all protons. Helium is 2 protons and 2 neutrons. So you can't just stick 4 hydrogens together, it could be 4 protons. So you have to somehow convert protons to neutrons, but that violates a principle of physics, conservation of charge. So that means there has to be several steps in between that allow nuclear fusion to occur. So that's what we'll be talking about next, is the physics of nuclear fusion.